So we have already learnt in the size reduction. We have seen different mechanisms of the size reduction, like your mechanisms of heat transfer, like convection, conduction, radiation. So we have already seen that every particle, when it is getting deformed or getting reduced from the coarse particle size to fine particle size, they are having two approaches. One approach is that the material is containing a flaw that is a weak spot. That weak spot is receiving an impact. Because of the impact and compression, the flaw will become a crack by little bit deepening. The crack will be receiving a further impact. During the time, it will be having a further deepening of the crack. It will be resulting into a crack. So the crack is developed into a break. So the flaw is converting into a crack. Crack is becoming a break when you are repeatedly hitting the particle with a hard object. So in our compressional force, we are going to apply the upper punch. The upper punch is going to come down and hit the particles, and it is going to compress and give the impact. All of a sudden, within seconds, these events will be occurring. If the particle is having a flaw, it will be converting into a crack, then it will become a break, and it will be cleaved into a small particle size, and it is getting deformed. The second mechanism is that the material which is receiving an attrition, the friction between the two particles and the die surface, they will be having a attrition. Because of the attrition, surfaces are getting chipped and edges will break. So these two are the mechanisms which we have already seen. We are converting a bigger particles into the smaller particles and making them into a deformed state. Now, we are going to apply some theories of this powder deformation. If you see the above concepts, the Griffith has stated that almost all particles solid contain some flaws most of the times. So in our pharmaceutical powders, whatever we are going to deal, they are containing the flaws and the microscopic cracks. Microscopic crack means they are not visible to the naked eye, but when you are observing under the microscope, they will be seen. So a flaw is a structural weakness that may develop into a crack under the strain when you are giving an impact or a compression. So which will be eventually resulting into a small particle. This is one category of solids which are present in the first group. That is in the Griffith series, the first group of the material. And the second group of the material, when they are undergoing the powder deformation, the flaws are present, not present in the second group, but the flaws can be created by, new flaws can be created by the impact. It means in the first group already existing, the flaws are getting present on the surface and they are converting into a cracks and breaks. In the second category of the material, according to Griffith theory, if the flaws are not present, the force of the milling creates a new flaw, then that will become a crack and it will become a break into a small particle. This is second category. The third category in our pharmacy is very tough and they are not having at all flaws, and it is very tough in nature. So not all the material exhibit the brittle behavior like above two. Some material resist the fracture even at the much larger stresses. Because of these, they are tougher in nature, they will be very difficult to break. In that particular case, we are going to face too much of trouble in the tablet manufacture because they are not getting deformed and they can be made into a capsules easily in that particular time. We will be delivering the particular drug mixture in the capsule form because very tough in nature and they are difficult to make as a tablet. We are going to make this, and generally we are having some other materials approaches like a granulation. We can convert them, this tougher material, into by adding a binder, and this binder will be making a granule will be compressed into the tablet. This is one approach also we can do. So among these, the first category of first theory of your Griffith is providing already flaws. They are weak in nature and they are undergoing the deformation easily. In the second group, they are not having a flaw, but a flaw can be created. It is a medium in nature in the size reduction and deformation. The third category is the toughest job, where it is very difficult to get the deformation even under the high forces. Generally, they undergo the plastic flow, which allows the strain energy relaxation without crack propagation. It means that even though they are having forces are applied, they will be behaving as a elastic material. Most of the times these material, they are tough in nature and elastic in nature. Elastic in nature, you may be thinking that when they are flexible, what is the problem? You take a rubber band, when you stretch your rubber band, what will happen? It will be getting stretched. But the problem here in this particular case, when you leave it, it will not become a crack, and it will be again coming back to its original position. It means even if you apply the impact, if you apply the compression also, what do you do when you are stretching it or you are holding it tight in your hand, they will be getting compressed. But when you are leaving, just like your sponge, if you are keeping it and making into a one ball-like structure in your hand, and you relieve it, again it will go to cuboid shape of your sponge. In this particular case, what will happen? The elastic nature of the particular one, it will not break the particle without crack propagation, because crack is not getting propagated, break will not be occurring. This is the reason this type category of material very tough to make them in a form of a tablet. When the plastic flow occurs, atoms and molecules slip over another, and this process of deformation requires the high energy. That high energy is actually named as a yield point. Beyond the yield point only, these material can be broken. Otherwise, they will come back to their original position. Take the example of your rubber band. When you are stretching your rubber band and leave it, the rubber band will be stretched to the longer distances. When you leave it, it will come back to the original position. But when you are stretching over a particular force beyond that particular limit, it will break. After that, it won't come back to original rubber band. It will become just like a straight line, not like a circular in nature previously what you are taking it. So once it is breaking a straight line rubber band, it will break into the two pieces. It means you have applied in the third category where you have applied the force beyond a certain critical force, which is called as a yield point. So this relationship can be given very much in the form of a curve that will be explaining the elastic modulus. So what is this elastic modulus? Why this third category are very tough to make it? Because their elastic modulus is very high. This is also called as modulus of elasticity. It is a quantity that measures the object or substance's resistance to being deformed elastically. Because why it is not getting broken? They have got a resistance to getting deformed. So they will stretch, again they will come back because of their elasticity. But in the tablet manufacture, we need to have particles in the form of plastic material. Plastic materials are the material, they tend to break after particular force, they tend to break it. But the elastic material, they get stretched and they will come back to original position. It means if your pharmaceutical powders are having a high elastic modulus, they will be getting compressed and they will become again powder after the upper punch is lifted, because they are not permanently deformed. They are temporarily deformed, and once the strain is relieved, so the stress will become zero and they will come to original position and they will be present as such without any deformation. Of how it is present, it will appear like that only. It means whatever the pharmaceutical powders which have got a high elastic modulus, they are very difficult to make them into a powder in the compressed into tablets. Now you may get the question, sir, in such materials, if you are handling in our pharmacy, what I need to do to give to a patient? In that particular case, we are generally preferring to give in the form of capsules, because capsule does not require deformation. Just you need to take the bulk density of the powder and take the volume of your body, how much volume each is required to put there, so that you will be having your dose is present there. So remaining volume till the body is present, you add a diluent and fill the body and keep the cap and close the capsule. In that particular case, such elastic material can also be given as a single dosage form. This is the concept we are going to take a decision by understanding these concepts, because you may be seeing in your pharmacy stores some powders or the drugs are existing as a tablets. Sometimes you are getting not in tablet form, you are getting as a capsules only. Sometimes you don't have capsules and tablets, you are having only syrups. So sometimes syrups are not at all existing. it is existing in form of only injections. So these are all the decisions whenever you are taking it. This will make a critical understanding of their original solid characteristics. Then we can take the decision that which drug can be given in what form. And we are going to see these physical properties and chemical properties and take the decision. But generally in the solid deformation, when we apply a stress to the powder, the elastic modulus of the object that is defined as the slope of its stress and strain diagram or stress and strain curve. In the elastic deformation region, a stiffer material will have the highest elastic modulus and very difficult to them to break and compress into a tablet. And now the question comes how to deal this issue or the case. So in this particular case, one thing is we need to remember that stress curve for a solid we need to make. So the stress curve for the solid which is appearing in this particular diagram, if you see it, what is happening there, you are going to have two types of axis. One is y-axis and x-axis. In the x-axis you are taking the strain and it is going to undergo the stress when you are applying the strain onto the powder. This is resulting into a stress strain curve for a solid, and the curve will be having two types of regions. One is the elastic deformation region, another one is plastic deformation region. So the stress curve for a solid, it is determining these two, and it is having in between one yield point. So this yield point is very much critical to us. Say for example, if you are straining your material by application of a force and they are undergoing the stress and making a radial, the force is existing in the radial direction and your axial direction, and they are making a deformation which will be taking place. But before the yield point, if you are applying any force like upper punch force, you are applying it, then what will happen? The elastic deformation will occur, and before the yield point, like a particular critical strain, that will again come back to your original position. It means you are compressing the powder when you are leaving your upper punch, and again the powder will become powder only without conversion into a tablet. You don't get, because elastic deformation. Now the question comes, if you want to convert such powder into a tablet, you need to apply the force, that is a strain, beyond your yield point. In that particular case, it will behave, the material will behave as a plastic in nature, it will break. It means you are creating a flaw and you are creating a crack, and it will become broken and it will behave as a plastic after yield point only. It means wherever the yield point is very higher and higher, we are going to have a tougher and tougher for tablet manufacture. This type of curve, it will be giving us the idea that can I convert that particular powder into a syrup or a capsule, or should I make it into a tablet? We can take a decision. So this is the one which you are going to study, the yield point, which is going to create a greater path to take a decision in which time I am going to make my doses for manufacture in research and development. If you see this elastic modulus has been given as a lambda here, which is equivalent to stress divided by the strain. So you are taking where the stress is the force causing the deformation, which is divided by the area to which the force is applied. It means force per unit area, we are applying the pressure. So the pressure is getting applied when you are applying the force per unit area. This is taken as a stress in the numerator, and in the denominator you are going to take a strain. It is the ratio of change in some parameter caused by the deformation to the original value of that particular parameter. Most of the times these stress is measured in the form of Pascals. So you are applying in the strain, you are applying some upper punch force by decreasing its distances. So you are applying the force. In this particular case, you are making the change in some parameter, the change in the force application, you are making it. So the numerator and denominator both are present. That is the reason it will become a dimensionless number. So if the stress is measured in the Pascals, then the strain is a dimensionless quantity, because we are taking the ratio of same parameter, whatever we are applying it, whether it's you are decreasing the distance in the upper punch, where the initial distance and the final distance, which are decreasing it down to compress the tablet, though distance by distance it will become a dimensionless number. So in this particular case, your lambda will be having a units of Pascal, that is elastic modulus is given in the form of a Pascal. It means you are taking this particular lambda value, which is giving whether it is increasing or it is present as a plateau, to see our material how they are behaving, and we can take the decision. So the stress and strain diagram in y-axis and x-axis, what you have already seen, this is going to give a either single phase, entire region of your strain, it is behaving as an elastic material behaving, or it is from the zero of your strain. Immediately after that, it is behaving as a plastic. Depending upon that, you can take that whether the material is tougher for you to reduce the size or make a tablet. This is actually what the journey which you have already studied in the B-Pharmacy pharmaceutical engineering section. So now we will be having the two stages which are uncovered during this particular powder deformation, that is a powder deformation. It is given as a power. It is a powder deformation. So the first stage is called as a elastic deformation. The second stage beyond the yield point is called as a plastic deformation. And we know that the elastic deformation is having some yield point. So the before the yield point, whatever you are applying the strain onto the powder, by decreasing and holding it down and applying a compressional force from the upper punch, then it is a reversible phenomena. Because of that reversible phenomena, you won't get any size reduction or your deformation occurs. But beyond the yield point, it will be converting into a irreversible phenomena, where it will be behaving as a plastic material, and we are going to have a plastic deformation occurs. It means if you want to make a tablet, you should have some plasticity in your powder. The material should behave as a plastic material, not like an elastic material. The plastic material, they tend to have some brittleness, they tend to get broken. But elastic material, they won't break, they will not have the strain propagation and crack propagation, and they will come to original position and make them very difficult for the tablet manufacture. But in this particular issue, yield point or a critical force what we are applying, that is going to be our target point, so that either we can be having a successful tablet manufacture or size reduction or not. Because beyond that point only we will have a irreversible phenomena. Because of this irreversible phenomena, we are going to undergo the powder deformation and tablet formation. In the powder deformation, you are converting first the material into a bigger material into a smaller particle. Again, they are getting bonded and it will become a bigger particle like a tablet. It means your powder is taking a journey of size reduction and size enlargement. Both are taking place in the tablet manufacture. But both need to be irreversible phenomena only. Because of that reason, GPAT question, you require a material characteristic, important material characteristic of your tablet manufacture, which you need to have is plasticity, but not the elasticity. Elasticity is the one which is not good to make a tablet material. The elastic material, they will be getting compressed and again they will become a powder after relieving your strain, after lifting your upper punch. This is actually what we need to understand. So this plasticity is actually what is decided by the yield point. If very higher yield points are present, and they are very tough to make them as a tablet, and very tough to make them as a powder size reduced. Most of the times we will be employing in the size reduction a cutting mechanism, so that we will be making them broken. And you know that your fibrous material, they are very tough to get compressed also, impact also, they will not be getting much broken, but your cutting mechanism, they will be irreversibly having it into a smaller powder. There you are able to employ. But in this particular case of tablet manufacture, even though you are getting reduced it by, again you need to get joined to get a size enlargement technique. It means you are having two approaches in the tablet manufacture. One is a size reduction and another one is a size enlargement, opposite phenomena. In the size reduction, quartz particle converted into a powder, and powder is made into a granule in the case of tablet, that is a size enlargement process, and granule is made into a tablet, again it is a size enlargement process. It means we are undergoing the size reduction, that is size reduction process, and going to size enlargement process in the tablet manufacture. All these stages which require the solid or the powder deformation, it will be getting deformed, its form is getting altered. Because of this particular reason, Heckel has made some plots and categorized all our pharmaceutical powders into 3 types. This is very important question, and you will be asked sometimes in the 5 marks question in the exam, or sometimes it will be added with the stress and strain diagram and the Griffith theory along with the Heckel plots as a 10 marks question in the powder deformation. So the powder deformation and behavior is based on your stress and strain plot diagram and your Griffith theory. And the second part of your powder deformation is the Heckel plot. What Heckel has done is that he has plotted the curves, and these curves, it will be giving the shape of the curves, it will be giving the idea that what the pharmaceutical powders are categorized into what category, type A, type B, type C, in which category the material is falling, whether it is a drug and an excipient, so that we can see that whether I am going to have an easy job to get converted into a tablet, or I need to go for a capsule or something else, I need to take a decision. Okay. Now, the powder packing with the increasing the compressional load when you are applying a upper punch, it is normally attributed to a particle rearrangement first, because when you are taking a particle getting compressed, the voids will getting filled with powders, and they are changing their shapes and their sizes, and they are getting moved to the voids, and the rearrangement will be obviously taking place. This rearrangement will occur even in the tapped density also. First you are doing a bulk density and just you are adding a powder into the measuring cylinder, but in the tapped density what you are doing, you are hitting onto the hard surface and repeatedly till the value is constant, because you are allowing particle rearrangement. This type of rearrangement will be happening in our pharmaceutical equipment also, because when we are operating a tablet compression machine under the high speed, they are getting vibrated. Because of that vibration, you will be having a rearrangement will be taking place, and voids are getting filled. So this increasing the compressional load, first they will be taking to the particle rearrangement. After particle rearrangement, they will be having an elastic deformation, but the elastic deformation is not resulting into any net size reduction or a deformation, but you are applying the force beyond the yield point, then it will undergo the plastic deformation. This plastic deformation is a irreversible phenomena, and you are going to have the powder which is broken and getting joined, and you will be making a tablet. Even after formation of a tablet, it will be, if you are applying more force onto it, again the tablet will break, and it will be resulting into a particle fragmentation. That is called as a brittle fracture. GPAT question. In this particular journey, when you are taking it, first what you are doing, you are taking a powder to desired size, and that will be done by the size separation. And in the size separation, you are taking the upper sieve and lower sieve, and in between you are taking the powder that is having an average particle size. That size, when you are putting into the punch, it will be rearranged, and voids are getting filled when you are tapping it or vibrating it. After that, when you are applying the force, it is elastic deformation before yield point, and after yield point, it is a plastic deformation. In the plastic deformation, your tablet is formed. It is a size enlargement process. After the size enlargement process is made, if you are applying further force, the tablet will tend to get broken, like a impact. When you are applying to any particle, it will be getting broken. This is called as a particle fragmentation. Again, the tablet will become a powder. This is the worst stage. You are preparing a tablet and breaking yourself, so you should not apply the powder beyond certain above force. Similarly, you should not apply the force less than yield point. It means you have got some region in your compression of a tablet. In that region, when you are applying the upper punch force, that is a strain, it will have the strain beyond the yield point and less than the particle fragmentation. This region when you are applying in the force, you will be going to get a tablet formed. So for that purpose, Heckel has done the analysis. It is a popular method for determining the volume reduction mechanism under the compressional force. What is this volume reduction mechanism? Whenever you are having upper punch is applied onto the die, and when the upper punch is entering into the die, it will remove all the gaseous or the air which is entrapped between the particles. The interparticular voids and the pores, intraparticular pores are present, that we defined as a porosity. In the previous class, what we have done? Percent porosity. Percent porosity means you have taken the true density minus your bulk density divided by true density into 100. That is your percent porosity you have already determined. It is containing interparticular voids, intraparticular pores. Within the particle, there are some pores are present. Between the particle, there are some voids are present. This is all getting reduced. The volume is getting reduced by the application of the force. So this volume reduction mechanism under the compressional force, what Heckel has done the analysis, he has found out that this process is first order process, first order kinetics, GPAT question. What is first order kinetics? Whenever the kinetics is following zero order, it is not dependent on any parameter. When it is following first order, it is dependent on one parameter. If it is a second order, it is dependent on the two parameters. If no parameter is dependent, it is parameter independent, then we are calling it as a zero order. But this Heckel analysis has proven that this powder deformation is a first order kinetic process with the interparticulate force as the reactant, the particulate force which are present as a reactant, that is a starting material, and the densification of the powder as the product, that is end product, that is the ending. So he has named this as a reaction, this powder deformation as a reactant or a reaction. In this particular case, the starting material is having higher pores, the ending material is containing the highest density. What is this concept in the why the starting material is having a high pores? Because they are not getting compressed in the starting, they are cutting the voids and pores in them. Because of that reason, they are having a highest force. But the starting material, when you are using a application of a compressional force, it will be getting densified. In the densified means the same mass, it is going to reduce its volume. So mass by volume is the density. In the case of densification, the powder is getting compact, and the powder is getting compact and made into a single tablet, and where you are removing all your pores and voids and filling with your solid material after deformation. And you are going to get a dense tablet that is having a least volume with the same mass. So this is your end product. By taking this process, and he has done some experimentation, and he has seen that according to this analysis, the degree of compact densification, compact means tablet densification, whatever you are getting, we are calling it as a compact. You may get the question, sir, is it a compact? Is obviously a tablet. Why are you not writing as a tablet densification? Why can't you write it as a tablet? But it is beyond your scope to get explain all these one. In the next year, you have got different types of tablet manufacture. That is, one is direct compression, one is wet granulation, another one is a dry granulation in pharmaceutical technology. When you are making a tablet in the exam, you will be asked to prepare tablet by the wet granulation or dry granulation or your direct compression. In the direct compression, what will you get? You take the powder, it is very fine in nature, and the fine powder you are converting into a compact tablet by directly compressing it. This is process is called as a direct compression first approach. But you have got the behavior of the particular material is elastic in nature and flow is not proper, and you don't get content uniformity. you are going to convert into a granule by adding water, and that is called as a wet granulation. So you take the duff mass and you convert into wet, and the wet mass is getting when the wet mass is getting compressed, when the wet mass is getting passed through the sieve, you will get a wet granule. After the wet granules are there, you are going to dry them and you are going to get a dry granules. These dry granules are converted into a tablet by the compression. This is second approach. And the third approach is that you take a tablet powder and make them into a slug. What is the slug means? It is a bigger tablet. Without application of your powder, any solvent, you make a compact. That is also called as a slug. The slug is broken and converted into granulation. That is called as dry granulation. It means the compact may be either your tablet or a slug. So most of the times the slugs in our factory, which will be using by the roller compactor. Most of the times you are having a compression rollers. You are going to have a roller mill, which you have already seen in the first semester of your second year. Roller mill, there are two rollers are present, material getting compressed between them, then you will get a compacted densification there. So if you are seeing this, the degree of the compact densification means the material which is falling in between the storal or the upper punch and lower punch, they are getting densed. Means their volume is getting reduced, density is increased with the increasing the compression pressure. How you have done in the previous sum, the compression pressure you could increase by decreasing the distance between the two rollers. That is one point you have done in the roller mill. In the tablet manufacture, what you are going to do, you make the decreasing the height between the upper punch and lower punch. There you are going to apply the more compression pressure. You are decreasing the height of your upper punch so that you will be having a more compression pressure. So it is directly proportional to your porosity as follows. What he has depicted as the equation is the change in the relative density per change in the pressure. So the relative density where your rho r, that is unit change in the relative density rho r per unit change in the pressure P, that is equal to or directly proportional to E porosity. If porosity is more, the change in the relative density per unit pressure is more. This is actually having a directly proportional relationship with the porosity. So we have already seen this is actually acting as a reaction in that starting material is highly porous and the ending material is a compact. So this is actually what we have seen. So the same thing which is kept as a equation is a equality by putting a proportionality constant called as a K. By multiplying E with a K, you are converting directly proportional relationship into the equality. Then you are going to get a Heckel first equation. In the Heckel first equation, you have got the change in the relative density of the powder per unit force change in the pressure is equal to K, that is proportionality constant, into E, that is porosity. How did you calculate the porosity? You have taken your true density minus bulk density divided by the true density into 100, you have got a percent porosity. If you are getting simply it is a ratio, then it is approaching to 1 or less than 1 or greater than 1. That is actually what you have already got it. If you are having a highest porosity, ratio will be very less. If you are having less porosity, it is approaching to 1. If your bulk density is approaching to the 2 density, then your porosity is 0. The percent porosity is going to getting a 0. So generally what you have done in the practical in this year, you have got around 60% porosity when you are having, because they porous in nature, they are going to have a reduction in the volume also. This is the first equation we are going to see. So calculation of the porosity which you are going to have by the equation, calculation of our bulk density and true density concepts, and by taking the porosity E is equivalent to -1 minus relative density. Here he has replaced E with 1 minus rho r, that is relative density. It is giving a second equation of a Heckel. In the second equation, when you replace the E, present K into E, you have replaced the E with 1 minus rho r. So E is equal to 1 minus rho r. So you are going to get the second equation, that is change in the relative density divided by change in the pressure is equivalent to K into 1 minus rho r. So after integration of this equation 2, you are going to get a third equation, that is Heckel third equation. Here you are going to get integration between the extreme ends. Then you are going to get natural log of 1 by 1 minus rho r is equivalent to Kp plus A. This is the equation you are going to get, and the Heckel equation 3. So it is appearing as y is equal to mx plus c. This is a linear equation, it is appearing here. So in this particular case, c is equal to intercept, that is nothing but a here in this equation 3, and m is equal to k, that is a slope, and x is equal to p, that is a pressure, and your y is equal to natural log of 1 by 1 minus rho r. This is your y. If you are plotting this by taking natural log of 1 by 1 minus rho r in the y-axis and the pressure on the x-axis, you are going to get a curve. The slope of the curve is equivalent to k, that is proportionality constant. The intercept of the curve is equivalent to a, that is intercept a. When you have got k and a, and you can easily calculate by the putting the term x in the pressure, and you can calculate the relative density, or you apply the relative density and you will be going to have the pressure calculated. So this is actually what you are going to get by having this determination of k and a. So with the Heckel plots, the behavior of all the material when you are applying these equations, and you are taking the curves of all the material, most of the material which we are using in the pharmacy, and Heckel has made the plots and categorized all our pharmaceutical powders into 3 categories. One is type A, type B, and type C. And you may be getting confusion now. Sir, what is this all? It is going beyond our head. So it is a bit confusion. When you are making a tablet, and your tablet journey of a compaction, when it is present in the next 5th unit, then you will be able to integrate this topic. Generally, it is required to be made along with tablet manufacture, then it will be easy to understand. But in the physical pharmaceutics point of view, you need to see the first powder behavior, then you can enter into the tablet manufacture. Without knowing a powder behavior, you cannot understand a tablet manufacture. That is the reason you are categorizing all our pharmaceutical powder into 3 types: A, B, C, type A, type B, type C, based on the equations and the curves. And then we are calling it as a Heckel A plot, type A, Heckel type B, and type C materials. So how they are appearing now we will be seeing. First we see type A material. Heckel type A material, if you see this diagram, compressional force P on the x-axis, natural log of 1 by 1 rho r in the y-axis, you are getting a straight line. This line is not showing any yield point. It is little bit curvy is present initially in the sleep region, and after that is going. It is just like a parallel line, linear line which is appearing. It means the material is already having a weak spots, and you don't have much yield point there. It means the material is behaving as a plastic material. It is not having much elasticity. So elastic modulus for this particular type A material is very less. So it is VG for example, this is the sodium chloride. A linear relationship is observed with the plots remaining the parallel as the applied force is increased, indicating that deformation apparently by the plastic deformation. There is no elastic deformation region in this. All material is behaving as a brittle material, and they are undergoing the plastic deformation. So this is the one called as the type A material. And according to Heckel, we have got a type B material. The type B material, if you see, initially it is having a highest slope. After that, the slope is getting decreased, and there is two joint, and joining of these two phases, it is having some yield point. It means initially they are behaving as elastic in nature. After the yield point, they are behaving as a plastic in nature. So type B Heckel plots usually occur with type B material occur with the harder material with the higher yield pressures, which undergo the compressibility by the fragmentation first to provide a denser packing. So the example is the lactose. So it is containing some yield value. After the yield value, they will be having behavior as a plastic in nature. So we are getting in this type B material, when you are plotting compressional force on the x-axis and the natural log of 1 by 1 rho r, that is the density, relative density. What is the relative density? And the change in the your true density minus bulk density divided by your true density. That is actually called as the relative density. When you have got the differences between your bulk density and the true density is the ratio, which is very high, then you have got highest porosity. When the bulk density and true density both are same, then porosity is going to be a 0. This is actually what is been seen in your practical, you have already seen. But in the type B particles, you have got some yield point. Before yield point, you have got some elastic material behavior. After that, it is having a behavior as a plastic. Lactose is an example for such type of the material. It is called as a type B material. The third, the material which is behaving as a elastic, after that, it is having a plastic behavior, and there is a plateau stage you are getting in the type C. The difference between the type A and type B and type C, if you see in the type A, it is continuously linear. In the type B, it has got two zones, and one is having a slope higher and another is having a slope lower. In the type C, you have got a linear with a plateau stage. So this is actually what is appearing with the material. They get melted in the lowest temperature and they are getting filled. The voids are getting filled by the voids which are present in the material is getting filled. So this is actually a behavior with the type C. For the type C material, there is the initial steep linear region which becomes the flatten out after application of the force. It is getting a flat region. Why this is having a flat region is this behavior is absence of the rearrangement stage and densification due to the plastic deformation and melting. Melting phenomena is present with the material like a magnesium stearate. So in the application of the force, you are getting a friction. In the frictional, you are going to get a frictional heat. In that heat, the material will be getting melted, and the melted material it will be entering into your void, and the void they are getting filled, and you will be having a plateau stage. After that, you will be having a type C of behavior where you have got a melting phenomena. It means you are going to have a elastic region. After that, you are going to have a region of plastic and melting. Both you are going to have plastic deformation and melting. Both are present. This is actually called as a type C material. And you may be getting questions and examples in the Google Forms and the multiple choice questions. What is the type A material, type C material, type B material, and where you are having a Heckel classification. Because of that reason, you are going to have a selection of this material, how it is going to be important for the manufacture of a tablet. That is going to be critical to us by this categorization. So we know that one phenomena for the tablet manufacture is a plasticity. The material required to be present as a plastic in nature, and your elastic modulus will be less. And the second category of a tablet manufacture is a fluidity. Fluidity means it should be flowing it. The powder fluidity is required so that the material can be transported from the hopper to the tableting machine, providing the adequate filling of the dies to produce a tablet of consistent weight and strength. Otherwise, you don't get the same weight of a tablet when you don't have the material is flowing freely from the hopper. For that purpose, what we have done in the angle of repose, the powder flow can be improved by the incorporation of the glidant. So the glidant is like a ball bearing. They will be present in the powder. They reduce the friction between the powder. They allow the powder to go smoothly, convert the poorly flowing powder into an excellent flow. This is what you have done in the angle of repose experiment. But what the sample you have got in the practical, it is already excellent. So that is the reason no need to add a glidant. But generally, you need to add a glidant such as silicon dioxide. It is also called as aerosol brand name, and a talc, or by making the particles as spherical as possible by the granulation, whether it is wet granulation or dry granulation or spray drying. And the most popular method of increasing the powder flow is by the granulation. That is the reason we adopt wet granulation or the dry granulation. Where you want to adopt wet granulation, dry granulation, depending upon your stability of your drug with a solvent. If the solvent is damaging your powder by the hydrolysis or anything, if you are adding water, then you don't add water or any solvent, make a dry granulation. So you are making your powder flow. This is actually what you are going to have, a fluidity of a powder and a plasticity of the powder. These two characteristics which will be decided to make the tablet manufacture easy. So the fluidity can be enhanced by making addition of your tablet powder granulation with a gradient. And your plasticity can be enhanced by choosing the material which is having low elasticity, that is low yield points. Elastic modulus are low. In such cases, you are going to get a low yield point. Tablet manufacture is going to be very easy. After that, you are compressing into a tablet. So you will be going to have a size enlargement process by the consolidation. What is this consolidation after the compression is? When you are applying the compressional force, you are applying the strain. When you are applying the strain, you are getting consolidation by the two methods. You need to understand these two methods. By these two methods, you are going to convert lakhs of powder present in the tablet powder, converting into a single particle, that is tablet. So how they are going to have, there are two approaches. One is a cold welding, another one is a fusion bonding. Because of this consolidation two types, you are going to get a tablet. Otherwise, if these two are not there, even though your material is fluidized and your material is having a plastic in nature, you don't get a tablet. But obviously, when the higher forces are applied, these two going to be happen. Any one of this is going to happen. In type A and type B material, generally what will happen, when the surfaces of the two particles approach with each other at the separation distance of the 50 nanometers, then they are coming closer and closer. So just like your DLV both here, when the particles are coming and closer, they will be forming a permanent sediment. Like that only, when you are applying the force, the powders will be coming closer and the distance between the two particles is less than 50 nanometers. Their free surface energy result in the strong attractive force, like your van der Waals attraction force. Then the process is called as a cold welding. So without using of your heat, they are getting welded simply by creating a van der Waals forces of attraction, and the particle will be getting attracted and it will be present as an intact tablet. This process is called as cold welding. And the second approach is fusion bonding. In the fusion bonding, what is happening? This is a consolidation too. Application of the force resulting in the generation of considerable frictional heat. When you are applying the force repeatedly, your copper punch is moving up and down, and dye is getting friction, and the powders they are getting slided out and getting friction. Because of that one, you are going to get a frictional heat. In the frictional heat, it is sufficient to cause the melting of your contact area of a particle. This is actually material behavior of a type C of Heckel. And in the type C of Heckel, what will happen? They will be getting melted. The molten mass is forming as a fusion and bond with one particle to another particle by getting occupied in the pores and voids. So when the melt solidifies, the fusion bonding occurs, because the solidification of a liquid will be happening when your tablet is coming out of your dye, exposing to the room temperature, and it will be getting cooled. When it is getting cooled, the liquid will be getting solidified. The fusion will become again coming to original state of solid, and it will be getting bonded. This is called as a fusion bonding, which in turn result in the increase of the mechanical strength of the mass of the tablet. So these two approaches which will make the tablet. I hope you are taking the powder from the stage of your powder and making it a journey till your tablets are getting formed. But the issue in this